We've previously discussed what the row space, column space, and null space of a matrix are. I'll leave links to those videos in the description, but you can of course see their definitions here. Now that we understand these concepts, we're prepared to introduce what are called the four fundamental spaces associated with a matrix. In this video, we'll see what those four fundamental spaces are and prove some interesting relationships between them. In doing so, we'll prove what's called the fundamental theorem of linear algebra. We'll begin with a quick recap of the row, column, and null spaces. If A is an m by n matrix, so it has m rows and n columns, then the subspace spanned by the rows of A is called the row space. It's denoted like that, and it is a subspace of Rn, because each of the m rows will have n components. Similarly, the subspace of Rm spanned by the column vectors of A, that's called the column space, which we denote like that. Again, it's a subspace of Rm because each of the n columns will have m components. And then the null space of the matrix A is the solution space of the homogeneous linear system Ax equals 0. And this is a subspace of Rn. Each vector x satisfying this equation has to have n components in order for the multiplication to be defined. And it's denoted like that, null of A. Now you may wonder, how do these three spaces associated with the matrix A lead to four fundamental spaces? Well, it comes from the transpose of A. You may recall the transpose of a matrix is found by swapping its rows and columns. Although, more naturally, that may immediately make you think of six spaces: the row space of A, the column space of A, the null space of A, and then the row, column, and null spaces of A transpose. But remembering what A transpose actually is, you should know that the row space of A transpose is the same as the column space of A, since the rows of A transpose are the columns of A. Similarly, the column space of A transpose is the row space of A. So in this list of six spaces, there are actually only four distinct spaces. So eliminating those redundancies involving the transpose, we arrive at the four fundamental spaces associated with the matrix A: the row space of A, the column space of A, the null space of A, and the null space of A transpose. Now, you may find it strange that A transpose is involved here. There is another way to view the null space that involves A rather than A transpose. The null space of A transpose may also sometimes be called the left null space of A, because by definition, the null space of A transpose consists of all solutions to this homogeneous system, A transpose times x equals 0. But if we transpose both sides of that equation, we get this equation. The order switches because we transpose the product, and we take the transpose of both factors. So A transpose becomes just A, and x becomes x transpose. Of course, the transpose of 0 is just 0. And so we arrive at this equation. X transpose on the left times A is equal to 0. And so this may be called the left null space of A. So the null space of A transpose is a lot like the null space of A, but with the unknown on the left. And so it may be called the left null space of A. But for this video, we're going to continue regarding it as the null space of A transpose. Now, I want to reiterate the spaces in which these fundamental spaces exist. Beginning with the row space, that's the space spanned by the rows of A. And so the reason that exists in Rn is that here's our matrix A, right? It has m rows and n columns. And so each row, these things that are spanning the row space, each row we see has 1, 2, etc., n components. The number of columns is the number of components in the row vectors, and so that's why the row space exists in Rn. n. There are n columns, there are n components in each row. The null space, we know that consists of all solutions to this system, which we can write in matrix form, like this, and you can see that these vectors satisfying the system have to have n components for this multiplication to be defined, because this row with n components gets matched up with this column, which must have then n components. So the row space and the null space both exist in Rn, where n is the number of columns of A. And then just as the null space of A is in Rn, because A has n columns, the null space of A transpose is in Rm, because A transpose has m columns. And similar to the row space, the column space of A will be in Rm, because each column consists of 1, 2, up to m components. There are m rows in A, so each of the columns will have m components, and so those column vectors spanning the column space exist in Rm. Another way to view the column space is that it consists of all vectors b, so that A times x equals b for some vector x, in which case we see this multiplication necessarily produces a vector with m components existing in Rm. So those are the fundamental spaces associated with an m by n matrix and the Euclidean spaces in which they lie. So now we wonder what relationships exist between these fundamental spaces. First, we're going to investigate the dimension of these spaces and how they relate. And much of this has to do with the rank of the matrix A, which you should remember by definition is the dimension of the row space of A. And also recall the dimension of the row space we've previously proven is the same as the dimension of the column space. So those are important things to know. The dimension of the row space is called the rank, and so we will call it the rank occasionally, but we're going to just write it as the dimension of the row space, just to keep our focus on the row space. Okay, so beginning this discussion on the dimension of the fundamental spaces, we've previously proven this result for an m by n matrix A, that the rank, which is the dimension of the row space, plus the nullity, which is the dimension of the null space, is equal to n, the number of columns. We've previously proven this, link in the description, but it can easily be justified by writing it in this way. If we reduce a matrix to echelon form, which as we've discussed doesn't change the row space or the null space, the number of leading variables in that echelon form is the rank. It is the dimension of the row space, since it is the number of non-zero rows. On the other hand, the number of free variables is the dimension of the null space. When trying to describe the null space, each free variable gets a coefficient vector, and that number of vectors is the dimension for the null space. And of course, the sum of these numbers is n, the number of columns, because each column either contains a leading one, and so is counted in here, the number of leading variables, or the column does not contain a leading one, in which case it corresponds to a free variable, and so is counted towards that number. So each column is accounted for exactly once, thus this sum is equal to n, the number of columns. So the dimension of the row space plus the dimension of the null space is indeed equal to n. Now let's consider A transpose. The dimension of the row space of A is certainly equal to the dimension of the column space of A transpose. Since A transpose results from swapping the rows and columns of A, the row space of A is in fact equal to the column space of A transpose, so of course their dimensions are equal. But since we know the dimensions of the row space and column space of a matrix are the same, the dimension of the column space of A transpose is the same as the dimension of the row space of A transpose. And so in total, this equation shows us that the dimension of the row space of A is the same as the dimension of the row space of its transpose. Then we can apply this result that we just discussed to A transpose. The dimension of the row space of A transpose plus the dimension of the null space of A transpose must equal the number of columns of A transpose. Since A has m rows, A transpose has m columns. But then also, the dimension of the row space of A transpose, we know that's equal to the dimension of the row space of A. And thus we get this equation. The dimension of the row space of A, which is the rank of A, plus the dimension of the null space of A transpose is equal to m, the number of rows in A. Altogether, we get this set of equations regarding the dimensions of the fundamental spaces, and this is the first part of the fundamental theorem of linear algebra. If A is an m by n matrix with a rank of R, then these are the dimensions of its fundamental spaces. The dimension of the row space of A is R, because that's just the rank by definition. The dimension of the column space of A is also R, because we know the dimensions of the row and column spaces are the same. The dimension of the null space of A is n minus R. That comes from this equation. Just subtract the dimension of the row space, which is R, from both sides, and we get the dimension of the null space. And then the dimension of the null space of A transpose, this comes from this equation, is equal to m minus r. Just subtract the dimension of the row space from both sides. And so we see that the dimensions of the fundamental spaces of a matrix can be determined purely from the rank and size of the matrix. M is the number of rows, n is the number of columns, and r is the rank. The next relationship between the fundamental spaces is more geometric in nature, and is the second part of the fundamental theorem of linear algebra. In order to discuss it, we need to introduce one new term. Here's this definition. If W is a subspace of Rn, then the set of all vectors in Rn that are orthogonal to every vector in W is called the orthogonal complement of W, and is denoted like this, sometimes read as W perp. Here are two sketched out examples in R squared and R cubed. If this line through the origin is a subspace W of R squared, the orthogonal complement is this perpendicular line through the origin, consisting of all vectors that are orthogonal to every single vector in W. In R cubed, if we have this subspace W, which is a plane through the origin, the orthogonal complement consists of all vectors in R cubed that are orthogonal to every vector in W, which is a line perpendicular to W passing through the origin. It shouldn't be a surprise that a subspace and its orthogonal complement have nothing in common except the zero vector, since the only vector orthogonal to itself is the zero vector, and for a vector to be in a subspace and the orthogonal complement, it would by definition have to be orthogonal to itself. So the intersection of a subspace and its orthogonal complement only going to be the zero vector. With that term defined, we're prepared to state the fundamental theorem of linear algebra. Let A be an m by n matrix with rank R. Then, these four-dimension equations we just discussed are true, and also, the row space of A is the orthogonal complement of the null space, and the column space of A is the orthogonal complement of the null space of A transpose. So the dimensions of all four of these spaces are determined purely from the size of the matrix and the rank of the matrix, and they also have this geometric relationship that they exist as orthogonal pairs. The row space and the null space are orthogonal complements in Rn, where remember n is the number of columns, and the column space and the null space of the transpose are orthogonal complements in Rm, where m again is the number of rows. So what remains for us to do is to prove this part about the orthogonal complements. Here's the proof of the first orthogonal complement relationship, and we'll go through the details of this. Once we prove this, it will easily follow that the second relationship is true as well. So what we need to do is prove that every vector in the row space of A is orthogonal to every vector in the null space of A. So let's begin by thinking about the null space. We're going to consider the homogeneous linear system corresponding to the m by n matrix A. The solutions to that system, of course, make up the null space. The system looks like this. The coefficients a11, a12 up through a1n, those entries are the first row of the matrix A. And of course, in total, there are m rows, hence m equations. Similarly, there are n unknowns. Each column of A corresponds to an unknown, x1, x2, all the way up through xn. As we've previously seen, we could also write this homogeneous linear system in dot product form. Each equation can be written as the dot product of a row of A, so row 1, with the variable vector x. Row 1 dot x would just be the sum of the products of their corresponding components. The first entry from row 1, times that first variable, x1, plus the second entry from row 1 times the second variable component, x2, and so on. It's just a dot product that's equal to 0. Similarly, the second equation can be written as the second row dotted with the variable vector, and all the way up to the mth equation, which can be written as the mth row dotted with the variable vector. And of course, they're all set equal to 0. And again, each Ri is the ith row vector of A. Then, from these dot product equations, and recalling the definition of orthogonality, we see that the vectors in Rn that are solutions to Ax equals 0, the solutions to this system, are precisely the vectors in Rn that are orthogonal to every row vector of A, because all of these equations, every single one of them, the whole system, needs to be true. The vectors that are orthogonal to every row vector of A, those are the solutions to this system. And of course, by definition, those are the vectors that make up the null space of A. And the row vectors of A that are orthogonal to those null space vectors, all of these row space vectors, of course, by definition, form a basis for the row space of A. So altogether, what this shows is that every vector in the null space of A is orthogonal to every vector in a basis for the row space. That's almost where we need to go. We need to show that every vector in the null space is orthogonal to every vector in the row space. So now we just need to show that follows. So our claim here is since every vector in the null space of A is orthogonal to every vector in the basis for the row space of A, that basis being the set of the row vectors, it follows that every vector in the null space is orthogonal to every vector in the row space, not just the basis vectors, but all of the vectors. All right, that's what we're claiming. Let's quickly justify it. So let's take an arbitrary vector u from the null space and an arbitrary vector v from the row space. Since v is in the row space, it can be written as a linear combination of the basis vectors, a linear combination of the row vectors. So u dot v can be written like this. U dot that linear combination of the row vectors, which is used to express v. But the dot product distributes across addition, so we can write this as u dot, that first term in the linear combination, plus u dot, the second term in the linear combination, and so on. Now in each case, we could take the scalars from the linear combination, k1, k2, and so on. We could slide those out and just have them getting multiplied by the dot product of the vectors. And in this way, we rewrite it as k1 times u dot r1 plus k2 times u dot r2, and so on. But of course, we know that every single one of those dot products is equal to 0, because we already established that every vector in the null space is orthogonal to the row vectors of A, the row vectors which of course make up the basis for the row space. Since every dot product is equal to 0, this whole thing is equal to 0. And so the original dot product, u dot v, the dot product of an arbitrary null space vector with an arbitrary row space vector, all of those dot products have got to be 0. Hence, by definition of orthogonality, every vector from the null space is orthogonal to every vector from the row space. So we've proven that the row space of A is the orthogonal complement of the null space. What remains is to prove that the column space of A is the orthogonal complement of the null space of A transpose. And perhaps you can see that this is actually an immediate consequence of the first result, because the column space of A is just the row space of A transpose. And so we could just apply this result again. Here that is written out by the thing we just proved. We know that the row space of a matrix is the orthogonal complement of its null space. So the row space of A transpose is the orthogonal complement of its null space. But the row space of A transpose is the column space of A, because the rows of A transpose are the columns of A, and thus we've established the second relationship that the column space of A is the orthogonal complement of the null space of A transpose. And so we've proven both parts of the fundamental theorem of linear algebra, the first part relating the dimensions of the fundamental spaces to the size and rank of the matrix, and the second part relating pairs of fundamental spaces to each other as orthogonal complements. This theorem is often summarized visually in a diagram like this. One space is representing Rn, remember n's the number of columns, and the other space is representing Rm. M is the number of rows of the matrix. We can see that in Rn, we have these orthogonal spaces, the row space of A and the null space of A. The spaces are orthogonal complements. They only meet at the 0 vector. The dimension of the row space is R, the rank of the matrix, and the dimension of the null space is n minus R. Together, their dimensions make up the entirety of Rn, the dimension of n. So if we combined all these vectors into a single set, together they would span Rn, because that would be a set of n linearly independent vectors. Similarly, in Rm, we have the column space of A, which is the orthogonal complement of the null space of A transpose. The column space of A has dimension R, the rank of the matrix, and the null space of A transpose has dimension m minus R. Together, we would have m linearly independent vectors that would span all of Rm. Since the subspaces of Rm are orthogonal complements, they meet only at the 0 vector. So those are the fundamental spaces associated with a matrix, and that's how to prove the fundamental theorem of linear algebra, which tells us all about those interesting spaces. If you want to learn how to find a basis for these fundamental spaces, I'll leave links in the description to my lessons going over that. Let me know in the comments if you have any questions, and be sure to check out my linear algebra course and linear algebra exercises playlists in the description for more. If you found my videos helpful, please consider supporting what I do by joining Wrath of Math as a channel member. You can get early and exclusive access to additional videos and extra practice, and if you join at the premium tier or above, you can access the lecture notes used in my courses. Thanks for watching.